so what I will, and this will be, my apologies, it's quite disorganized, so I will just jump around some code and try to explain what's happening. So yeah, in Lean 4, we have this environment which allows you to define your own extensions to what the system is showing you when you're doing maths. And one of those allows you to draw commutative diagrams for statements in the language of category theory. And so I wanted to, first of all, I mean, I'll show how it looks, but then I wanted to actually explain like the entire pipeline, how you produce a diagram, with the purpose that maybe some of you come to the work group later, then you have already some understanding of how it's working, and you can discuss how to make it better. So first of all, is the font size okay, especially in the back? Can you see it? So I define that types form a category. I guess that's in MATLAB somewhere, but just for the purpose of the demo. And then what you can do is, well, yeah, that. So our goal here is that f followed by some identity function is equals to g, followed by some identity function, and there you go. There's a square. You can also show it as a triangle if you want, which maybe makes less sense, but you can do it as well. So those are the two things we can do, squares and triangles. So that's the first thing. We would like ideally to support things other than squares and triangles. Let's go on to more examples. This is also just a triangle, but the point of this is that the layout algorithm can actually handle like long names, so it will scale the diagram correctly and all of that, which is actually slightly non-trivial.
Can you visualize stuff in the context?
Yes, I will get to this in the next one. So here's some random example from Sina. So by default, there is, okay, so now I can start explaining how you actually use this. So you can, there's a couple ways, but one way is you put this, before you start your proof, you put this command with panel widgets, and then you tell it which kind of widgets to show. And a widget just means kind of a visual component that appears on the right-hand side here. And previously I was using the goal type panel widget, which just shows you specifically the target type. But you can also use the selection panel, which means that if you select something, so the way you select something is shift-click on it. So I shift and then click. Then all the selected things will be shown as well. So okay, at this point we can discuss another limitation. Currently they are all shown separately. That is, I have one diagram for one equation and another diagram for another equation, but maybe it would be better if we pasted them together and just put those two triangles into a cube or square. And this updates dynamically, so when you move around in the proof and you change the goal state, then you'll see that happen in real time, which can be helpful to understand what you're doing. So that's that. I think this demo is roughly the same. You just we have some assumptions and we can visualize them as triangles. Okay, so then how does this actually work? And how do you write your own? That's kind of the point. So the pipeline is there's 3 stages, or you can think of it as being in 3 stages. First there's extraction, then there's layout, and there's rendering. So extraction is the stage which takes a substatement in the type theory of Lean and turns it into something that can be used by some diagramming software. Then we have layout, which basically puts these things on the Euclidean plane in some sensible way, like a triangle rather than, just have that be somewhere out there. And then rendering, which is just showing it in the browser, because this is actually a browser, this part. So for layout and rendering, I will start with that. We use a library called Penrose, which is developed by some people at CMU, not including me. So I'll show you Penrose, like what the purpose of it or how it works. So here's an example of another diagram that you can draw using Penrose, and this is, I guess, saying that F maps A to B, and then you have some subset of V of B, and the pre-image is over there. It's subset of A. And so how do you produce such a, because Penrose is a generic diagramming software, and it's optimization based. So the way you kind of phrase things is first you define your domain. So this is the file I have open here. The domain allows you to specify some types. So in this case, we have sets and points and maps. In the domain of commutative diagrams, we have objects and cells. Then you can produce some constructors, like here you can form a singleton set from a point. And then there are other ways to combine sets, and finally you can define predicates in order to give them some properties. So that's the domain, and the other two parts of a Penrose diagram are style and substance. So maybe I'll start with substance here. So substance is a specific diagram. So a domain is supposed to define like a domain, right? So in this case it's sets and subsets, whereas a substance is really a specific F and A and B. And so here it's declaring that A and U are sets, and so on. And there's some subset relations between them, and you can put some LaTeX for the labels. And the style program is probably the most interesting. I will not describe all of this stuff, but basically what you do in this style program is you define an energy or a potential, if you want. And as I mentioned, this is optimization-based software, so it will try to minimize the energy. And the idea is that the energy is supposed to be higher the worse the diagram looks, right? So we can see this process actually happen by dragging this thing here. So the initial state is pretty much randomly sampled coordinates. So there's some, so that circle is over there, and it has a random radius and so on. And then the optimization algorithm will kick in, and it will slowly try to minimize the energy in order to make the diagram look nice. So that's how that works. So that's some demo from the Penrose team. And for the commutative diagrams, I have written an analogous style program that tries to somehow encode what it means for a commutative diagram to be nice. But this is actually kind of complicated, it turns out. There are lots of tacit conventions that people use in paper, like things go left to right probably, and top to bottom. But also, you know, if you're drawing a pullback, then like some of the arrows are curved usually, but why? And so on. So optimization is tough to get working for. I mean, we can discuss it later. Maybe it's actually possible. So in the end, what I landed on is the description of energy is actually is hard coding quite a lot of things. It's not really trying to lay things out too much. You tell it explicitly, like this thing is to the right of that thing. So let me show that next. Any questions so far? So here's how Penrose is integrated in Lean. We can draw Penrose diagrams. Here is a simple example of a Penrose triple. So we have a domain which just has one type of blocks, and then we have a style program which puts at each block it draws a circle and it draws an equation that contains the label of the block. And then we put one constraint in the energy part, which just says that the label has to be contained in the circle. And then I described a specific diagram which contains a block B and some label for it. Right. So we can do this. And then for commutative diagrams, I have a DSL and style programs, which maybe I can show the DSL. So DSL, there's some super type, doesn't really matter, but there is a type of objects and there's a type of cells. And for any two things, you can connect them via cell. So this actually would allow you to do like higher category. You can do two cells as well. And I think 2 cells is the most it supports right now, but in theory you could go on with even higher maps. And then there is a collection of predicates, which, as I mentioned, are somewhat hard-coded. So it's not really, you can't really just say, you know, let these things be objects and connect them via arrows and then ask it to optimize it nicely. You have to say this is to the left of that thing. So we can say that that some map goes from left to right, or some map goes from, I think up means down, top, bottom to top. Maybe I should name it better. And there are some predicates for like curving things and labeling them, and monomorphisms, epimorphisms, and embeddings. And the style program, I think I want to go Oh, yeah.
So why is it that so like when you showed Penrose, it was dynamically placing circles and stuff like that.
Yeah.
Why is it that here you need to say whether they're going up or where the positioning of the things are and so on, right? It seems like Penrose should be able to handle just dynamically creating this graph.
Yeah, so we can discuss that maybe in more detail later, but in short, the optimization process depends. This is also true of like machine learning. The initialization vector is actually very important. So for instance, suppose you're trying to draw a pullback diagram, and suppose you happen to start with this layout. I mean, okay, this is kind of a nice layout already, but suppose you started like this, okay? So this is the cone, and ideally, you know, if you wanted to make the diagram nice, this thing, so let's call it W, this thing W would end up here, right? That's the way you usually start. Conventional way. Yeah.
That's how conventional way of drawing pullbacks, right?
Right.
All of us do that.
Right. But the software just samples it randomly, the initial positions, and suppose, which does happen, I mean, it can happen, that W kind of lands in this center of the square. And then to end up here, you'd have to kind of move like that, right? But there is a part of the potential that says two objects should not be too close to each other. So there's like, you can imagine like a hill here that you can't really get over. So things like this happen. We can discuss it more later, but that's like roughly the...
So you want to have a kind of a planar representation of some kind?
Say again, sorry?
You want to have some kind of planar representation included in your description of the diagrams?
It contains layout.
More information, yes, than just pure information.
Yeah.
About the layout.
Well, that's an unfortunate practical consequence. Ideally, you wouldn't have to do it.
Sure.
Yeah.
Okay. That's the way it is now.
But right, yeah.
Okay. Thanks.
But I mean, you could, like what you're describing here is like a drawback of if you did use dynamic layout, you might get slightly suboptimal things for pullback cones.
Yeah.
But like, that still seems better than not, you know, having to generate all of this data from scratch. From like doing this in the.
I mean, some of them end
part.
up looking really weird, is the problem. Like, because you know, so when you're trained on textbooks, you have pattern. You're good at pattern recognition for specific things, and then you see this and what, right? So it's a question of how helpful is it.
I mean, there could be different levels of precision.
Right.
But,
And you say you don't have pentagons or hexagons quite yet.
We could draw a pentagon, but
For us,
maybe I should clarify that statement. Actually, I will get to this. But basically, for the extraction part, we don't have much. So the layout is actually kind of okay. You can draw complicated shapes. The layout and rendering part, but we don't really have too much code that takes type theory and turns it into descriptions of diagrams. So that part is only scarce in terms. So we can lay out some more complicated things. So here I wrote down the description of a pullback. And so, you have to do some layout there. So you start with some objects, right? There's and they're unlabeled here, W is the low at the top left corner, and P is the pullback, and X, Y, Z are these things that form the cone. And then we have a bunch of arrows, and then we say which direction each of those arrows goes. And we also say that I and J should be curved, which they are here. And finally, we display some labels a little bit, and that's more for styling. But you can see that this label is like slightly to the left of the arrow.
You could describe this using an energy function. Right? Like you could say that, oh yeah, this arrow wants to come in from this angle because, you know, it's a pullback square and it's opposite of the pullback direction. So you'd like to go in that, you'd like that guy to live on that side of the thing rather than the other. And then these things are curved because if they weren't curved, then they'd be hitting the lines and so on. So you don't want really tight angles, right? So you want to leave.
Right, but then, so this arrow, for instance, you probably don't want to leave any possibility that it's curved, right? This arrow here.
Well, and it's part of a pullback square, and squares are supposed to have straight sides. So you have some energy associated.
So besides that, the other thing is, so one thing is you might not be able to get over a potential hill when doing optimization. The other thing is that it can be expensive. like the more constraints you add, the more complicated potential becomes, and then you have to do optimization for a long time to actually. So if you saw in this demo earlier, at least for squares, it's pretty much real time. I mean, it takes maybe half a second or something, but it's reasonably quick, right? Whereas if you start optimizing really hard, then it might take a minute or something, which is not great for interactive proof.
What I'm saying is you shouldn't like immediately say, oh yeah, this will be too slow before you build the thing.
Oh, I tried it though. It was slow, but we can try it again. So let's do it in the work group.
Yeah.
I mean, so the Penrose team have also optimized their algorithm, so it might work better. Yeah. Right. So back to this. So we can do this kind of thing. I think we could do a pen. I'm not sure if I want to try it right now, but you can specify diagonal.
What I like is what I want is cubes, right? So,
Cubes are interesting as well, because cubes are, so that's we were discussing this yesterday with a few people. Cubes are not usually on the, maybe don't want to draw it on a grid, since if you draw it on a grid, you might end up with two vertices on top of each other. So you want to be slightly, like have it be slightly rotated. I don't know. So cube, right? Well. And what am I missing? No, that's the cube, right? So this, I mean, the distance between, like this distance is not the same as that distance, so it's not exactly grid-based, but maybe you can think of it.
I was being an user and saying that's what I want for some bits of category theory that I need to kind of.
Yeah, no, exactly. So for instance, pullback map is sort of a lemma that is ideally visualized as a cube, because you have one pullback and another pullback, and you're getting a map between them, and that's good. But yes, cubes would be good. Okay, so that's the layout and rendering parts. So again, we're using Penrose. Other options are possible, but that's what it's doing right now. And then back to the first stage, which is extraction. So you have some lean type theory, and then you want to turn it into some description of a diagram. So how does that work? So I've written some example here of one such function. Let me go here first. So the thing you write is what's called an expr presenter. I don't know if this is a great name, but it's supposed to present an expression. Okay? And it has a name. So this one is going to draw, I should call it pullback cone. It's going to draw pullback cones. The layout kind doesn't matter so much, but you can have block layout and inline layout. And then the function itself is just supposed to take some type, which is expra, so it's a lean expression in the type theory, and it's supposed to extract from it some layout if it can, otherwise it fails, and then you just don't use it. So we can see first how it is used in this example here. So in this example, I'm going to construct, so I'm given a function f from natural numbers, and I will, which is actually a category morphism. And I will construct a kernel pair for it. So basically the pullback of f with itself. So again, I'm using this with panel widgets thing to make visualization possible. Then I do some construction, and I'm trying to prove that this is a pullback. So at some point in this proof, I will end up with a pullback cone, C. So I actually have to rename it because it wasn't typed as a pullback cone, but whatever. So we can click on C, and then we see the pullback cone there. And so yeah, F is being pulled back by, well, so this isn't, to be clear, this is like another cone, so it doesn't have to be the pullback cone. So maybe I should clarify what pullback cone is for those that don't know MATLib. That just means, so if we're forming this pullback here of F and G, then a pullback cone just means a pair of cones like H and K that commute, but it's not like the pullback, so it's just some math there. Right, and that's what we're seeing here. So how does the extraction work for that? Now I go back to the pullback presenter. So that's the top level function, and then calls this thing pullback cone, n question mark. That means, is it a pullback cone, question mark? And it runs in a monad, hence the M. So this takes a Lean expression, and then what do we do? So we first grab the type of it, because in the example I was showing, actually let me in the example so that we can remember what it was. So, okay. So in the example, E is going to be C, I mean the local assumption C, and then we take the type of C and call it ETP, and the type of it is limits the pullback cone FF. Then you need this instantiate mVars thing, which I won't discuss too much. And then we check, is this type actually of the form pullback cone with a bunch of arguments applied to it? And if it is, then we get f and g, which are the two functions that it's a cone over, that form the span. Right. And if that is the case, well, if it fails, then we just return nothing, so we kind of fail to produce a diagram, but if it worked, then we have this f and g. And then we can use make app m to construct the two projections, c dot first and c dot second, which both start at the point of the cone. And then we use some function type question mark, which basically takes some expression in the type theory, which is of the form, Hom type AB, and gives you the A and gives you the B. So that's what these two lines do. And now we have all the objects that we need to actually produce the diagram. And the way that works is we write a Penrose program, which in this case is hard coding 4 objects, and 2 cells which form the code, and then 2 other cells which are the I and the J, so the first and the second. And you have to match, so this is maybe seems tautologous, so let me call this like AA or something. You have to assign to each object in the Penrose world some Lean theoretic expression. So in this case, we have an object Z, and I assign to it the codomain of this object, which I call AA. And the point of that is that this diagram includes information about what these things were, so you can click on them and maybe do other things like that. Yeah, so that's how you turn an expression into a diagram. I understand that this might not make any sense if you've not really seen too much Lean, but hopefully I that will make some sense. And I think that's all I wanted to show. So